please.
Ah, good. So, welcome back, everybody. And so today I want to discuss with you a thing which the theorem which I just touched on, one of the main theorems of the area, the so-called Chakaloff-Bayer-Teichmann theorem. So let me remind you what this theorem is about. Okay, so it's in the lecture notes. This is Jenya, we can hear you.
Oh, sorry.
No problem. I just tell you. So the theorem is theorem 3.1 in the notes, and this is telling us the following thing. So given a sequence of putative moments, so the M01 we put 1 just for simplicity, and we have given M of them, then and we assume, so it's an assumption, there exists a P realizing M, then there exists L1 times LD plus 1 and P1 till PD plus 1 greater where the later are greater or equal to 0, and the sum over the Pj j equal 1 till d plus 1 is equal to 1, such that the sum j equal 1 till d plus 1 of Pj delta j, so let me call it L, PL delta L realizes as well. So what I mean with this, so this probability at the point J is just given, sorry, I made a mistake here, so I have to, okay, so let me correct that. So okay, let's call it I, cannot call it L, so it's I, PI, and then here, correct that, Li, yeah, so that means that this probability as a function of J, so how it looks like, it is equal to PI for if I'm at the place Li and 0 otherwise. So I have d plus 1 places in which I have some probability and the rest is 0. And this is an extremely important theorem, although it's somehow the proof is rather easy. It's surprisingly recent. I think it's from the 90s or maybe even from the 2000s. Although the original proof by Chakaloff is much older. It's from the 40s, but he had a kind of compactness assumption. That means that he proved it only, for example, like we had before in a finite set of integers, not in an infinite set. So all the difficulty comes from the fact that we actually work with an infinite set of integers, and then this thing is actually surprising. For a finite, it's not so surprising. It's just reducible to classical theory, and Bayer and Teigman just noticed that you actually don't really need this kind of restriction. And why this theorem is interesting, it just somehow looked that we assume what we want, because we're just saying that we assume that we have a realizing P. The usefulness is that it tells you what form you actually have to look for. If you want to decide that some moments are realizable, then the theorem tells you can always do that with a probability which takes only d+1 values. And that immediately leads you to a numerical strategy. You just have d+1 values. You have then to try out, to work to try to optimize this, at which L you put this probabilities, but at least you don't have to start with infinitely many numbers. You reduced everything to a finite thing, and so there's a good chance to get about it with some numerical approach. Also, this theorem is important for another reason in numerical analysis. It's called the cubature, and it's one way of numerically treating complicated integrals. So if you want to treat an integral, and the only thing you care about that you're correct integrating polynomials up to degree d, then it is sufficient to solve the moment problem, and the best way is solving it in this kind of discrete ways, like I have it here. And this gives you then a very easy numerical algorithm in order to compute integral, and that's done frequently. There's more. People spend a lot of time about the Gaussian curvature, and this you can do in more general. And I'm not an expert in it, so I don't know details about it. So don't ask me. But that's one application of this. So let me now try to prove this theorem. Okay. And the interesting thing of this theorem is the proof is quite quickly going in some abstract realm. So we have the strategy of the proof is, that first I show that I can have that I get a representation like that, and then I first do this, and then I show n is less or equal, can be chosen less than equal d+1. Okay, so how we do that? So the first thing is just recall that I have this delta L. What is this delta L of J? Delta L of J is 1 if J is equal to L and 0 otherwise. So this is somehow the building blocks. It's a probability where all probabilities are one way. Or if you think about linear algebra, this is just nothing else. It's a canonical basis. So you can understand why somehow that is a good building block to start on working from. What is the moments of this primitive measure? So if I look at the moments of this measure, it's just L to the K. So this lead me to do gives me the following idea to introduce the following set. The set C is just the set of all the sum of all I equal 1 to n of alpha I, and then I have here Li squared. So I write all the moments Li d, and I do this for some n for all alpha e greater or equal to 0 and the sum of the alpha E is equal to 1, and the Li have to be in N0. And this is now, if you look at this, is a vector with D entries, so this is a subset of RD. Now I claim the following thing, that M1 till a vector M1 till MD, which let me call this M underline, is realizable, is equivalent realizable by a finite combination of delta L's, is equivalent to the fact that the M is contained in C. So I have now a set theoretical description of what it means to be realizable. Note, we introduced last lecture the notion of convexity, and note that C is a convex set. But why this is true? This is true because if you just think a moment about this, what I have here, the alpha I L1 Ly to the D, and I forgot to put up the chat, so so please feel free to ask any questions. I will try to watch it, and please, anybody, feel free to point out if I missed to see it. Something is in the chat. So I look at these. What is this? These are just the moments of this probability. Alpha I delta Li I equal 1 to N. Yeah, and so you see, if I have a measure which can be written as a combination of finitely many delta L's, then the moments have to look like this. If I have a vector which can be written in this form, then these are the moment of this measure. So it's exactly this kind of set. Now, okay. Now so that's other things which we want. Now, let me give you a definition of the set of all M realizable by a probability on N0. Okay, this set D is given by all vectors M1P to MDP element of RD such that MPK is equal to the sum J equals 0 to infinity of JK P of J for some P. This is essentially a tautological definition. And you can easily check that D is also a convex set. Now, the interesting thing is, so that leads us into convex analysis, but essentially the main things which you use of it, it's topological properties, which have very little to do with convex analysis, and so I will avoid to use convex analysis. And that's the first thing you have to show is, I left you to exercise 3.3, is that D is a subset of the closure of C. So remember, C is the one we want. We want to show, actually, what we want to show, that any realizable measure is in C. Any realizable moments are in C. This is not exactly true, but you will see what is lacking. But the first thing you can see, if you look at the closure of C, you will get all vectors in D. What it means that anything which you have here can be approximated by something in C. Okay, and that I leave as for you as an exercise. I want to show, in some sense, the opposite. I want to identify the interior of C. And I want to identify this as a subset, no, interior in the sense of the topology of RD. Okay, I have a claim, so I just guess what it is. I mean, that's difficult. I mean, that's like very often in mathematics, you are actually come up with this claim is the main part of the work. And if you see the proof, you will understand how you would come up with this kind of claim. So I will try to explain you in the proof that you would end up with something like this, even if you don't know it from the outset. So you take all this vector, so this is the same, and now you want to have that that this is true. You need an extra condition that n is greater to D, and that's important, that alpha I are strictly greater than 0, and somehow the rest is the same. And I need to assume that they're actually different. I mean, before you were always probably thinking that they're different, but here I need to be logically correct. I have to assume that. Okay, and so what I want to show is that, what is easy to see is that U is open. No, it means U is open in ID means that you can move in all directions a bit and you don't get out. And you see that here, that if you change the alpha i's a little, you will not move out of your set. So U is open. The question is, so that's somehow an intuitive way of seeing that. And I want actually to prove that this is really an open set in the topology. So the first thing you have to note is that the collection of vectors L1 to D up to, let's say, LD to the power D are linearly independent. And there are several ways of seeing this, and one of this is what we are doing exercise 3.4 is you look at a kind of modified fundament determinant. So you write all this kind of vectors in a determinant in a matrix, and you have to show that this is unequal to 0. And actually there's a formula for this. This has an explicit formula, and the product of 1 less or equal to I less than j less or equal to d lj minus li. And so you see, if they're different, this determinant will be unequal to 0, and hence you will get a set of independent vectors. Okay, so let's try to show that U is open. So take U, which is of the form alpha I, li squared to li to the d. Now in U, and now define epsilon as the minimum of alpha 1 till alpha d. So what we want to show for continuity, we have to show there exists an R and a ball of radius R around U such that this is contained in U. Now, for this, we need some controls over the lengths of vectors. So assume I have a vector. I make no difference between row and column vectors. So assume I have a vector B1, BD, and I define V as the sum I equal 1 to D, beta I, and then I have here the vector Li to Lid. So what is then the length? So what is the length of the vector? So the length of the vector is equal to the sum k equal 1 to d v k squared. Okay, so to express this, I write this here as a matrix with a product with B. And so from this, I see that my matrix A, K, I has to be equal to L, I to the power K. And so if I put that in here, I see that I get the sum K equal 1 to D. Then I get another sum J equal 1 to D, A, K, J, L, beta J, I get this squared. And if I calculate that out, I can write that as a sum K equal K and J equal 1 to D of A transposed multiplied with A. So I have actually here, because of the square, I have 3 sums. One of them goes in this matrix matrix multiplication, and then I get beta K times beta J. So I get the following quadratic form. Now I notice that A transposed A is symmetric matrix, and hence it can be diagonalized. And let me write the eigenvalues of lambda 1. Let me order them by size. Okay. And so by a coordinate change, and so by an orthogonal, by a coordinate change, by an orthogonal matrix, so let me call this O. So I have that beta, or let's say O beta is equal to a new vector X, and in this new vector, in this new coordinates, I have that the matrix is diagonalized. So I see that this is equal to the sum I equal 1 to d lambda I xi squared. Now I can bound this below, just because the squares are all in a negative, I can bound this below by the sum 1 to d lambda 1 of xi squared. So I can take that, I can take this out, and then by the orthogonality, I see that this is the same as lambda I, the sum I equal 1 to d bi squared. Okay, and this estimate from here to here, where this is lambda 1, this is what I will use in the following. Okay, so now we're almost there. So let W be an element of the RU. Okay, but now I can write W as in the following way. E1 to D gamma I Li up to Lid. Why I can do that? Because I showed before that these vectors are linearly independent. And so any vector can be written in this form. So, okay, so that's, now I have to show, want to show that W is in U. Okay, and for this one, I need to use the only thing which I know, that is the norm of this difference. So let me first write this difference. So what is this difference? Remember, they have both a representation via this basis, so you could write them both like that, with Li to Li to the D. Now, so let me write the norm of this to the square. We know that this is because here, because of our assumption that we're in the ball, we have this inequality. But now I can use this inequality which I have here above, so I can write that as lambda 1 times the sum. And what are the betas? The betas are just the coefficient in this expansion. So it's just gamma I minus alpha I squared. And in particular, the sum of non-negative things is always larger than each of these summands. And so square. And so what I see is that gamma k minus alpha k is less or equal to r divided by the square root of lambda 1. And this is true for every k. So in particular, this is true for the maximum over all k's. Okay, so why I want to do that, I want to show that W is an element of U, and that means what it means. It means that W has the form gamma I Li to Li to the D, and these ones here are strictly positive. No, that's what I want to know. I don't know that. Yeah, that's what I want to find out. But I have some, but I know that the alpha case, I know that the alphas are strictly positive. So if this distance is small enough, I should be in the game. So let me formalize. So what I want to show is I want to show that gamma k is strictly positive. Okay, so what I do, the only thing which I control is the difference to alpha k. So I write it like that. And now I want to bound that below. Alpha k is non-negative, so there's nothing to be done. This difference, I don't know which sign it has. So I can bound it below by minus the modulus. Now this is a general kind of inequality. Every number is always greater or equal to minus itself in the modulus. But I defined epsilon as a minimum over all alpha k's. So it was a minimum over the k of the alpha k's, and here I computed the maximum, so I get this kind of inequality. And so for r strictly smaller than epsilon times the square root of lambda 1, I get the result. Now then this is strictly positive. And this implies then that W is an element of U. So we showed, so U is open. Okay, now I left to you as an exercise, again, 3.5, to show that actually D is contained in the closure of U. So what we have, so let me recapitulate what we have. We have U, and we have that U is a subset of C. And C is a subset of D. So these are the one which we do. This is realizable by finite. This is realizable at all. And these is, one could say, realizable with positive coefficients. Okay, and now I see that the closure of this one is containing the largest of this, and so it means that U has to be the interior. So is the interior of C and also of D. Now you could ask yourself, okay, but why do I actually care? What is the interior? Why I'm interested in this? Okay, I've promised you to say so you see why we had the assumption that the alphas has to be greater or 0, because it comes from here that if I change the gammas a bit, then I have to have some space. And you see also that this only works in finite dimension. In infinite dimension, this will not work. So this this is something which is really bound to the fact that we have finite many moments. Okay, now the next thing which I want to use is when an realizable M is in the interior. Okay, and I leave to exercise 36, 3.6, which is very similar to what we have done before. So what you are in the interior if somehow we are in the interior of D. So let MP just which is M1P to MDP, an element of D. So moments which come from a probability. And now you need one extra condition to be in the interior. You need that if you look at the set of all J element and 0, such that P of J is strictly positive, if this has at least D elements, then MP is in the interior of D. And you can imagine that a proof of which is very similar to what we have done before will give you exactly this kind of will you get exactly this kind of property, because it just means that if you have you just have P places in which you slightly can change the value of your probability, and so you can move in all directions, and this will effectively allow you to create any moment which is in a ball around this kind of point, just doing more or less the same kind of estimates which we have done before. It's not exactly the same. So what does it mean? So what we have, so that means these MP are then in U, but elements in U can be written as a finite combination. So now, so what we have, so we solved the problem if we have this kind of extra condition. How we can do now the general case? So for the general case, so let P be a probability that realizes. And then we define J as the set of all small j's in N0 such that P of J is strictly greater than 0. And now what we do is we replace in our argument above N0 by J and repeat the argument. And that works. And then we see exactly these are cases where actually you don't need the maximal number of deltas to do the constructions. You get actually away with less than D. And that's what in the general proof cause you some kind of problems. And the result will then be finished. So the second part follows from the following general theorem for convex sets. So this is essentially the dimension theorem from linear algebra, but for convex sets. So the most important theorem in linear algebra is that if you have a vector space, then there exists a number D such that you can find D vectors so that you can write every element of the vector space as a unique linear combination with respect to these D vectors. And any other collection of vectors which have the property that you can write every vector of the vector space uniquely has also to have exactly D elements. That sounds very obvious, but trying to prove is not so easy. And the same is true with the Kara-Theodori theorem, which is somehow the version for convex set. So it's let V be a vector space and the dimension of V, this is a finite dimensional theorem, is called D. Now I have a family of vectors. So I have VI, I, element I. So it's a family of vectors. Now, if I have a V in the convex hull of these vectors, so V is a vector which I can write as a convex combination of these vectors Vi. And if you remember, the only restriction was that I'm only allowed to use a finite numbers of vectors, but nobody said that I cannot only use a limited number, like which I will show now. It is D1. So a vector, so then I can show the following, then V is an element in CoV if and only if V can be written as the convex combination of D plus 1 of the vectors in vi element I. So that's so it means if you can write it as a convex combination. So remember, let me call you what is a convex combination. It's I write it as a sum alpha I vi, and alpha i's are non-negative, and the sum of alpha i's are equal to 1. And I probably have now convinced you that this is the right thing to use for this kind of problems, and it's that only finite many alpha I are actually non-zero. So it's a relatively finite sum. So it's a so the convex combinations, like linear combinations, is only allowed if you work in an algebraic context only of finite linear. So not the important difference to what you have in linear algebra. In linear algebra, you can find one set of d vectors to write it as a convex, as a linear combination. Here you have somehow d plus 1 vectors. That's not so surprising. I will make a picture afterward to see that. But you cannot choose one fixed one. You may have to choose different ones to do the job. So let me give you an example. So for example, if as convex set, so if your set vi, if your collection vi I element I is just, let's say you take the set of all vectors x in R2 such that the length of x is equal to 1. So let me add a page. So this is just the unit circle. So what is now the convex combination? So it means you take, for example, a point here and a point here, and then you add the segment between them. So this, okay, and then you take a point here, and you take a point here, and you take a segment between them, and so on, and so on. And so you see that the convex combination, so this here inside, that will be, let me call this set A. This will be the convex hull of A, will be the entire disk. And you see that each vector inside you can actually write as a combination of two. You just take a point, then you take another point on the boundary, you draw the line, and then the point you need as a second point is the one which you find going through this line. So in this case, you can do it actually, you can get away with 2 instead of 3. But if you, for example, if you set vi I element I is if the set is just 2 points, so then it's 3 points, then the convex hull of this is everything you can write as a linear combination of 2, but then you could also take a point here and a point here and write this as a linear combination, or take a point here and a point here, write this as a linear combination. You see, you get all the triangle. And the points in the triangle you cannot write as a linear combination of 2, you need at least 3. And in the exercise, the problem which I tell you about the non-uniqueness start to happen if you look at 4 points. So if I make the combinations of 2, I get somehow the boundary. And the convex hull is all the interior of this square. And so, but there you get it that you cannot choose 3 fixed points. So here, anything what you have, you can write as a convex combination of these 3 points. In this case, you can't do that. And so using that for our theorem, so the Karat-Theodori gives us the result. And with this, I finish my 5th lecture. I thank you all for the attention and also for all the questions you gave me. And I hope you can take something from it. I have the solution. We will publish the solution next week for the exercise. I corrected some typos in the exercise, so please look at the newest version, which should be on the OneDrive. And yeah, and please send me any emails if you have any questions.
Okay, many thanks, Tobias, for your lecture and for the whole mini course. And let's thanks Tobias using our virtual hands, or as always, you can type thanks in the chat. So do you have any questions now?
I think you need to stop the recording.
Yes, and we'll see if, yes, now I can do that, yeah. Yeah.
Are you sure?
Yes. Oh,